Welcome to the EOL seminar. It's my pleasure to introduce today's speaker, Dr. Jenna Samra. Jenna got her BS and MS degrees in electrical engineering at Penn State University, and then her PhD in applied physics at Harvard University. She was an associate research staff at the MIT Lincoln Laboratory, and now she is an astrophysicist at the Smithsonian Astrophysical Observatory. Her research focus is the development of optical instrumentation for solar and atmospheric observations. And so she was involved in the development of an airborne infrared spectrometer for solar eclipse observations. And that instrument flew on both of the eclipse field campaigns that EOL was involved in. And I think we will hear how that all went down today. And with that, I will pass it on to you, Jenna.
Thank you so much, Rike. I'm so excited to be here and to share with EOL how our eclipse campaigns went. So my presentation is high altitude instrumentation for observations of the solar corona in the infrared. First, I just want to make a note that everybody can email their questions to Rike's email address right here, and we'll take them at the end of the presentation. So I'm going to talk today about our Airborne Infrared Spectrometer, AIR-Spec. This is the instrument that we flew on the 2 Eclipse campaigns on the Gulfstream V. And we have plans for a modified version of this instrument to fly in 2020. And this is the Aspire campaign for those EOL people who are familiar. So the Airborne Infrared Spectrometer measured 9 magnetically sensitive coronal emission lines in the 2 previous total solar eclipses from your Gulfstream V aircraft. I'm going to talk a little bit about the motivation, especially because this, I know the G5 flights are not often used for solar physics research, so I thought it might be interesting for you guys to hear exactly what we were learning from our flights on the G5. I'm going to talk about our instrument design and some of the challenges and how we improved it. I'll talk about our eclipse observations and try to give you a picture of what it was like on the plane during totality. I'll talk about our science results and then where we're going with the instrumentation from here. So on the, of course, there's the G5 down below, and on the right is a picture of our instrument on the G5 being filled with liquid nitrogen that's producing a big cloud of water vapor on the airplane. So the AIR-Spec is meant to study the solar corona. So I'm going to start by giving some background on the corona. Why are we interested in studying it? Well, first of all, the solar corona is the outer atmosphere of the sun. It's pictured here on the left, if you can see my mouse, and I'm going to just point out a couple of features in this image that are pretty interesting. So we can see that there are a lot of structural features like streamers and loops that I've pointed out here. We also see that the corona can be viewed in different wavelengths of light. In the gray, black and white image we have, that's just broadband visible white light. The colored image in the center is actually extreme ultraviolet light, around 30 and 17 nanometers of light. And so that already is pretty interesting. It's giving us a hint that the corona is potentially quite hot because it's able to emit at such short wavelengths. And in fact, if we look to the right, we do see that the corona is much hotter than the surface of the sun here, the photosphere, even though it's less dense at the same time. So now if we zoom out, we actually see that in fact the corona extends quite far into space, and we can see these structures extending, and so that also wouldn't be possible if it were in equilibrium. And so this gives us another clue that the corona is very hot. And the broadband visible light that we see here is actually due to free electrons. So the electrons, the corona is so hot that the electrons have been ripped off of many of the atoms. And so there's charged particles in the corona. There are electrons, and then there are ionized atoms. And the electrons scatter light, and that scattered light is what we see during a total solar eclipse. We also see in this zoomed out picture, we see some hints here that the corona might be dynamic, right? So this is, although you can't see, this is actually something moving. It's what we call a coronal mass ejection. So this is plasma and magnetic field that's being ejected off of the corona here. And so we can look at some examples of coronal activity in these 4 movies here. So on the left, we see a solar flare. This is energy released from the corona in the form of light. And then we see the 2 rightmost images are material being ejected from the corona. So this is actual coronal plasma, charged ions and electrons. And then here we see some loop structure after a flare eruption. It's plasma actually precipitating back down to the surface of the sun, but it's following these interesting loop lines and kind of the same structure that we saw in the previous image. So it turns out that there's a kind of a unifying underlying theme to all of this: the heating of the corona, the structure and the dynamics, the loops and the streamers that we saw, and the energetic events. And this is all being driven by the corona's magnetic field. So those loops are actually plasma, charged particles, electrons and ions. They're following, because they're charged, they're following the magnetic field lines, and they're tracing them out so that we can see them. And so it turns out that actually, if you want to model, if you want to understand what the corona looks like, for instance, if you're trying to predict where to look during the next total eclipse, you do it with a magnetic field model. And so here's on the left, this is a model of the 2017 eclipse made by Predictive Science Incorporated. And then this is the intensity that they got. And here's the a processed image of the eclipse in white light. And so again, white light, electrons are scattering white light off of, they're following the field lines, and then they're scattering light from the photosphere, which is the surface of the sun that we see that supports life on Earth. And that's how we're able to see the corona during an eclipse. Unfortunately, even though the coronal magnetic field is really important, it's very difficult to measure. It's very weak. So one way to do this, possibly one of the most effective ways, is to measure the polarization in light emitted from the corona. And so this just shows an example of Steve Tomczak at HAO, his instrument COMP. And you can see that with some pretty long integration times, we can get information on the magnetic field. But it's challenging, and the signals are very weak. And so what we want to do is explore what potential emission lines would be useful for measuring the magnetic field in the future. So this is kind of the background to, now this is where our instrument is going to start to come in. So when we talk about an emission line, what we're talking about is an electron in some kind of ionized either iron or silicon, sulfur. There are a lot of different elements on the sun that produce these lines. So the emission line is caused when an electron, a bound electron in this ion, drops in energy, and from one energy level to another, and the difference in energy is emitted as a light of a particular color. So it's a photon with a particular wavelength. One really great example of a bright line in the corona is the green line at 530 nanometers. When this line was first discovered in the mid 1800s, it was seen during an eclipse. People thought it was a new, actually a new material. They didn't know what it was because they had never seen iron that had been ionized 13 times. So iron that had lost 13 electrons, what we call iron 14. And so because this particular wavelength didn't exist in any neutrals, they thought maybe it was a new element. It turned out to be just iron, but with 13 electrons missing. And so we're looking for similar things, not this green line, but similar lines in the infrared. So basically from 1.4 microns to about 4 microns, we looked for 6 lines during the eclipses that covered that wavelength range. The reason that we wanted to look in the infrared as opposed to the visible or the extreme ultraviolet, you might think, you know, the corona is so hot, it's clearly emitting in the extreme ultraviolet, which we saw previously. That's true, but the infrared is particularly useful because for measuring magnetic field, the signal that you get from infrared light, it goes as it's a much stronger signal for the same magnetic field. So basically what we're looking for is how these wavelengths, how this line emission changes, how there's a splitting that happens in the presence of a magnetic field. And so we're trying to characterize these lines to see which ones might be most useful for measuring magnetic fields in the future. So our instrument didn't actually measure the magnetic field, but it measures the lines that we're hoping to use in the future to measure magnetic fields. And so we had sort of 4 measurement goals. Our line intensities we were able to characterize the lines to see which ones would be most useful for future magnetic field measurements. We wanted to look at the lines to get some information just on the physics of their formation themselves. We wanted to look for velocities to see potential events, dynamic events on the sun, and then we wanted to compare with satellite observations to get some general plasma diagnostics, so temperature and density. So the airborne platform that I'm going to talk about should be very familiar to you. This is the Gulfstream V, owned by the NSF and operated by NCAR EOL, the Research Aviation Facility. It has a 50,000 foot ceiling and it flies at about 500 knots. It's been outfitted, as you know, it's a pretty special Gulfstream V. It's been outfitted with these special viewports that we use, in particular a sapphire viewport to look for the infrared lines. But regular glass cuts off somewhere between 2.5 and 3 microns, and we needed to get all the way out to 4. And the reason that we're on the airplane, by the way, the main reason is that we're looking in the infrared, and as everybody is probably familiar with, the atmosphere absorbs a lot of infrared light, and so we wanted to be above that in order to get for some of our lines wouldn't have been visible from the ground. Of course, being on the airplane presents a number of challenges, and I'll talk about those. I just wanted to show a quick movie of our instrument going up on the airplane. It had to go in pieces. This is one of the challenges. So our bench had to be able to be broken apart and then put back together, and we needed to be confident that it would remain aligned. Okay, so here's a picture of our bench back together on the airplane. We have kind of four systems here. We have an image stabilization system up front. This mirror takes the light from the window. The window's out of the picture here. We have a telescope which focuses the light down into our spectrometer. The spectrometer splits the light up into its component colors, and then we have a context camera which tells us where we're pointed in the sun. You'll see a bit more about each of these later. There's just some instrument specs on the bottom. This is our optical design. So this is a pretty standard grating spectrometer. The entrance slit cuts out the one of the spatial dimensions of the light because we disperse wavelength along one of the dimensions of the detector, and so we can't have spectral spatial confusion. So we cut that out with a slit here. And then this is the layout on our detector for the 2017 flight. We have spatial information vertically, spectral information horizontally, and our lines show up spatially resolved in these rough locations. Now, the thermal design was incredibly challenging. So because we were observing out to 4 microns, we had to account for the fact that there was a lot of thermal emission that thermal emission was going to be dominating our background. So we took a number of steps to to deal with that. So one of them was cooling all of the optics to below 150 Kelvin. So when you cool everything to those temperatures, you have to store everything in a vacuum chamber to avoid condensation. So everything behind the telescope's not cooled, but everything in the spectrometer is cooled. We pour liquid nitrogen in through this tube, and it kind of flows under the bottom of this floor here, and then copper straps that are attached to the floor actually come and conductively cool. They're mounted to the optics. They conductively cool all the optics. But at the same time, you need the optics to not move too much. So they're when you chill the spectrometer, you don't want to go out of focus. So you end up isolating them with some fiberglass. So they're mounted to the walls, isolated by fiberglass, so that just the surface stays cold, but they don't move as much as they would have otherwise. The IR camera is cooled by its own internal cooler to 50 Kelvin in the second flight, and that wasn't quite enough. So we were able to make the background a bit lower by packing dry ice around the camera right here. So in the 2019 Eclipse flight, we were both filling liquid nitrogen in flight and packing dry ice on the camera. So it's not an automated instrument. It requires a lot of care and feeding in flight. So the thermal background in 2017, taking the steps that we took, reduced it significantly compared to if we had done nothing, but we still had a big thermal background problem. There were a couple problems. There was a lot of structure spatially and temporally, and the change in the background over time was actually on the order of or larger than our brightest emission line that we were looking for. So that was really challenging to remove. And the background itself was about 10,000 counts compared to this emission line of about 100. So 100 times brighter than our brightest line that we were looking for. In 2019, we made a big improvement. This was really a partnership with the camera manufacturer. We helped them define their testing, and they did the improvements to the camera. So they got rid of that structure. They reduced the background by a factor of 18 or so. And it made for a much higher signal to noise ratio in that flight. We also, another challenge of being on the airplane is stabilizing the image. So the G5, it's a pretty smooth flight when you're up there, but it's not when you're looking at something the size of the sun, which is half a degree across. You realize that actually the airplane's moving around quite a bit, and of course the Earth is rotating, so the sun is also moving across the sky, or it appears to be. So we needed to take all this motion out, so we built an image stabilization system. This is actually something that we're refining for 2020 and could be used for other instruments, not any kind of remote sensing instrument, not just AIR-Spec. So it takes gyroscope input and then also input from a GPS, which tells it where the plane is and therefore where the sun is. And then it kind of crunches the numbers and outputs it calculates the angles needed for our mirror to take out exactly what the plane and the rotation of the Earth were doing. And so then the mirror moves, and hopefully this beam into the telescope stays stationary. And we're monitoring this on our context camera. In 2017, we did not allow we didn't have any automation tracking on the image. We just had basically the prediction from the gyroscope, and that was because we weren't sure how the image tracking would perform, and we were not able to test the eclipse situation before the eclipse. So we did all these tests on the moon and the sun, and we wanted to be confident that at least the system would perform the same during the eclipse, even if it wasn't maybe as perfect as we wanted. And in 2019, we were confident that we could add the closed loop or the image tracking component. And so I'll show you a comparison of the three cases here: no stabilization, what we call feed forward only, so no image tracking, and then feed forward as well as feedback on the image. And you can see the significant difference between between each case. And here are our positions. So the black line in these images, I forgot to mention, this is the entrance to our spectrometer. Light that gets through the black line is the only, that's all of our science light. This is the slit that I mentioned a couple slides ago. So here's our slit positions on the corona during the two eclipses, and you can see that we were jittering a lot more in 2017, and in 2019 it was a large improvement. We also removed a couple of artifacts that we didn't know about in 2017. We had a couple of issues in our spectrometer, a ghost line or some ghost reflections inside one of our optical elements that actually appeared, you know, kind of as pathologically as possible, looked exactly like another emission line in our spectrum, and we actually thought it was, but we discovered that and removed it by just basically blocking our stray reflections with a little piece of aluminum. And then we also had an artifact, one of our mirrors. There's some hysteresis in one of our tiltable mirrors, and it wasn't quite connected to the adjuster and was bouncing, and in flight, probably vibrated by the camera chiller or something. It actually made the line look like it was splitting into two, which would indicate, if it were, could indicate a line of sight velocity, a Doppler shift, but it was just too large for that to be likely. So we tracked that down in the lab before 2019, and we were able to change the way we mounted this to improve that as well. So 2019 was a much better instrument that flew. So I'm going to talk about the eclipses now and kind of what we saw, or what it was like to be up there. 2017, we took off from Tennessee and we observed over Kentucky. It was a much quicker flight than 2019. It was, you know, most of the time was spent circling. I'll show a breakdown on the next slide. 2019, the longest duration was actually over the South Pacific, and so we had to fly over 2,000 miles from Lima, Peru, where we were based, observe the eclipse here, and then we didn't have enough fuel to return. So I mean, we planned to land in Easter Island, Rapa Nui, which is right here at the Red Star. So that was there was about a 5 or 6 hour ferry from Lima to the eclipse point, where, you know, we just kind of sat on the floor of the G5 and panicked. So it was two very different flights. So I just wanted to give you a taste of what it's like to observe the flight. So we had 4 operators on board from SAO, from the PI team, 2 or 3 RAF crew, and then the 2 pilots. And so the 4 members of the PI team, so here's kind of what they were doing. I'm here, I'm looking at the image stabilization data. I'm actually pointing the instrument to different places in the corona. Ed DeLuca was looking at the science data, so he's looking at quick look data of the spectra, and then not shown are Peter Steinmetz and Vanessa Marquez. And Vanessa was she actually had to move the bench back and forth in 2017, right up until totality started, to make sure that, you know, that as the angle of the sun changed, we were getting light into our instrument. Peter was going back and forth, communicating with the pilots as we headed into the eclipse, which was a challenge to get onto that path, and then communicating with us, timing everything, and telling us when, how much time we had left, and when we should move to the next position. So I wanted to just show you a video, a couple seconds. So Corey Wolf, our program manager for 2019, he took this video of my screen as we just entered totality. You can see how dark it is on the plane. So I just want to show you kind of what it was like, and then this picture here is just a zoom in version. So. Get close! Yeah! I'm gonna go in position. So hopefully you could hear that. So, it's pitch black on the plane, and remember in 2019 we hadn't tested our image tracking, so we weren't sure that we could actually. We had tested it on the sun, of course, the uneclipsed sun, and we didn't know for sure that it would actually lock. So when the sun goes to the center of the image, that meant that our tracking had locked it, and we were pretty excited. And then I moved to the first position, which is, you can see the slit here off in the corona. Of course, it's not actually useful to have the sun centered in the image because the slit is just over the moon at that time. So it was a really successful. Both eclipses were really successful. This is our 2017 flight. I kind of talked about the path already. One of the lessons out of this was that we didn't leave ourselves enough time to do all that we needed to do right before we entered this totality portion right here. We were kind of fiddling with the instrument, setting the spectral range, and even acquiring the sun was more challenging, than we had anticipated. And so what we did in 2019 that was different was we made these loops that the G5 that the pilots did to kind of get ready to enter the eclipse path. We made these part of our setup. So we made it so that we could observe the sun on these loops and do our setup during that kind of hour lead-in. And then we pointed at these 5 locations during 2017. In 2019, we had a lot more time. It was a 9-minute eclipse, and we got 7 minutes of data. And you can see we pointed here. We overlapped. One of our goals was to compare with satellite observations, and I'll show a little bit about that in the results. We overlapped with the Extreme Ultraviolet Imaging Spectrometer, a satellite-based instrument on the east and west limbs of the sun. This is our one of our slit jaw images. So this is our context imager in the background here, and those are our positions of where our spectrometer was pointed. I'll start talking about the data. This is just a kind of a quick look at what our data looks like. So I mentioned that we have spectral and spatial dimensions to our data. We only have spatial imaging along one dimension. So here, this is the limb of the moon right at the bottom edge, and you can see I've subtracted off a flat background here. But you can see our emission lines, and they start out brightest at the edge of the moon, and then they go off into the corona, getting fainter as they go. So this is about half a solar radius into the corona. So this is just to give you kind of an understanding of what our images look like. And then if we take a cut along the spectrum here, the spectral dimension, this is what our spectra, this is our 2019 spectra. So you can see a couple of features. First of all, we see 2 lines. This is a very tiny line there, but it's more obvious in some other observations. These lines, we believe, were first detected by our instrument. We don't think they've been seen before. And then these other 2 lines as well have been seen before, but were also measured by our instrument. This one, the sulfur 11 line and this sulfur 11 line make a density sensitive line pair. So by looking at the line ratio, the ratio of these 2 lines, we can actually learn something about the density of the plasma and the electron density in the corona. So that's very useful. And I'll show a little bit about that in the next slide. So some understanding of exactly how much atmosphere or what we expect the atmosphere to be is necessary to actually fit these lines. You can see that, like, for instance, this strong line here, silicon 10, one of its wings has this atmospheric absorption feature, and so to get really good intensities, we need an atmospheric model. But by having an atmospheric model, by the same token, we can actually get a really nice wavelength calibration. We can, because we know, we should know where these atmospheric features are expected to be. Here's the model that we used, the preliminary model that we used so far. We can also get a nice instrument line shape. So, how much does our instrument broaden each of our spectral lines? We can get that as well. It's something that kind of falls out of the fits. And something else that we can get is we have these overlapping grading orders in one of our channels. And so having the atmosphere actually helps us separate them out. So it was actually really useful to get some atmospheric absorption here. And of course, it was much less than it would have been. Both of these lines wouldn't have been visible from the ground. So being in the G5, but still having some atmosphere above us, actually turned out to probably give us better science results. So you can, this is just kind of the fit equation. I'm not going to go into it, but basically the idea is you have the emission lines here, but they're sitting on top of this background. And part of that background is the white light corona that you see with your eye, except it's in the infrared now. And again, that's produced by scattering from electrons. So that's kind of a smooth black body function. It looks like kind of like the or almost like a lower intensity version of the solar spectrum, the 5800 Kelvin black body. And our lines are sitting on top of that. They're the emission lines. And so if you take all that into account and you do some fits, you're actually able to extract intensities from the lines. And so these are line fits from 2017. Some of the there's been some changes since then, probably to some of these parameters. This is an old slide, but one thing I wanted to point out is that with a radiometric calibration, we have an approximate absolute calibration from the photosphere. You can actually compare intensities, and we're able to get some nice comparisons with models for the intensities. So this is a model from Phil Judge's 1998 paper, which we used in actually a lot in building this instrument, and you can see how our measured intensities compared to his. So in addition to just comparing intensity, something that's really interesting to look at is how the intensity changes as you go away from the edge of the moon. As you go further out into the corona, you expect the intensity to drop off, but it turns out that the infrared lines, some of them don't drop off as quickly as the extreme ultraviolet lines, and that's due to some different physics in the way these lines are formed. So the extreme ultraviolet lines are collisionally excited, and as the density drops off in the corona, as you go away from further out into it, you have fewer collisions, and so you have fewer you have a dimmer line. The IR lines, because they're in a wavelength region where the underlying photosphere is actually pretty bright still, they have some radiative contributions, and so they stay bright further out, and they also allow some testing, basically, of the models for the atomic physics here. So here you can see that including photo excitation is really important for modeling our strong line. And this is in Chad Madsen's 2019 paper. And then also in Chad's paper, we can look at some density diagnostics. I mentioned that we had a density sensitive line pair. So comparing the ratios of these two of our two sulfur 11 lines allows us to actually get a measure of the density in the corona remotely. So Chad was able to do this with some extreme ultraviolet lines in 2000 from our 2017 satellite observations. So this is not AIR-Spec data, but it's the satellite that was co-observing with us, ICE. And in 2019, once we added that extra line and got that density sensitive line pair, we were actually with some, after making sure our fits were kind of as good as possible, we were able to get some density measurements ourselves, and comparing with a model by Giulio Zalzana, we see that actually there's it's a pretty nice comparison. This is a preliminary result. We need to kind of do a little bit more on this, and we're thinking of publishing this soon, but it looks pretty nice to start with. And we also, from 2019, we have some Paul Bryans and his student Austin were observing this eclipse from the ground, and they have some density measurements as well from white light images. So we've just started comparing with them. That also looks like it corroborates what we're seeing, and so it's going to be exciting to put all that together in a paper. This is just a very cursory look at temperature sensitivity, just a kind of beginning to look into this. This just sort of shows that, in fact, we do have some temperature diagnostics in the lines that we observed in 2019. So each of these lines, these emission lines, forms at a different temperature. You can kind of imagine that it takes a hotter temperature to rip more electrons off of off of a given ion than fewer, and then depending on the ion, that also plays into what is the formation temperature of each of these ions. So the sulfur 11 line here is a lot hotter than the iron 9 line, and so they kind of give us a way to look at the temperature of the emitting plasma. So we can see that if you compare, for instance, the observations 4 and 5 here, we see that the iron 9 line is weak. That's mostly just because it's a weak line, and you're a bit far away from the sun in these observations here. But there's a big difference in the sulfur 11 lines. So it seems that the region 5 is probably hotter than region 4. And in fact, if you look at satellite data, in compared to different temperature lines there, that seems to be what we see. So we have to do a more detailed analysis on this, and Chad Madsen did some of this for the 2017 data. I haven't shown it here. We can probably do an even nicer job on the 2019 data. It's higher quality, and again, we would compare to the extreme ultraviolet imaging spectrometer. So that work is also ongoing. So I want to spend a few slides on our future plans, because I titled this talk High Altitude Instrumentation. It wasn't just about AIR-Spec. And I wanted to put in context kind of where we're going from here. So we've measured these emission lines. We haven't measured magnetic field, but that's the ultimate goal. This is really a pathfinder instrument. And so, what's the path? What's the next step on the path? So one thing that we're going to do, our more immediate future plans, are 2 more Eclipse flights. We've been funded to fly the December 2020 Eclipse that's coming up very soon. And we have designs on the 2024 Eclipse that crosses the US as well. So in 2020, we submitted and were funded for a major research instrumentation grant from the National Science Foundation for ASPIRE, the Airborne Stabilized Platform for Infrared Experiments. And so what this does is it basically takes our image stabilization system and makes it a bigger aperture, and also separates it so that it doesn't depend on our instrument in any way. So anybody can use this after we're finished with it, after we prove it out in the commissioning flight. So it provides a 20 centimeter beam, so the 30 centimeter mirror at a 45-degree angle, and so that it's our existing telescope was a 10 centimeter telescope. So this is 4 times the collecting area, and so this is really enabling not just for the next eclipse, but for future eclipses as well. So here's a model of what we're planning to fly on the G5 in December. This is our same old instrument here. The new telescope is a bit bigger. We have a new narrowband imager, so we're going to get something like like this image here. This just shows the field of view. So we'll actually get science from our context imager. So here's the entrance slit, but now this is scientifically useful instead of just a white light imager. And kind of maybe most importantly, we're going to prove out this stabilization system with this large aperture mirror. And so once that's done, then this kind of, the part that I've kind of boxed off here is actually going to be, able to be used again and again for different instruments. And one instrument that we're excited about is a collaboration with HAO for a 2024 Eclipse flight. And potentially what we would look for here is to do a survey of the lines in the IR corona. So potentially a spatially resolved Fourier transform spectrometer instrument. We're talking with Phil Judge and Jim Hannigan about this. And the idea here would be to learn what lines are available in the corona in a really wide wavelength region. And the Eclipse is kind of perfect for this, because you're not going to necessarily, you're necessarily time limited on an eclipse. So you're not likely to catch an energetic event or something like that. But for just surveying what lines exist, you need to be above the atmosphere, and especially if this is a prototype or a pathfinder for future space-based instruments, and you need to be you kind of like as long a duration as possible. So the G5 is really enabling for this, because it gives us a bit longer than just being on the ground. We can follow the Eclipse path. So we're excited about this. We're going to prove out the image stabilization system in 2020, hopefully, and then we're going to propose to NSF after that commissioning flight for a new instrument to replace all this with a new instrument. And then we have kind of a bigger departure from what we've done so far, is a plan for a future high altitude balloon. And so this would be a NASA balloon that actually does measure magnetic field. So we're finally coming to, bearing the fruits of all this, this work to characterize these lines. So this would be a high altitude balloon with a coronagraph and a spectro-polarimeter. We've been designing this for a proposal that's due in August. So we've been looking at it in detail recently, and we took the tack of just adding a whole lot of lines here, because it's a really challenging instrument, even to just do, maybe like this 4 micron line, which was interesting to look at. And so if you can add the other lines for some added complexity, but it seems to be, it makes it a much better pathfinder. And so that's the tack that we took. And our data looks something like this. So we have a lot of something like 100 slits, which means we can get spectral and spatial information in this dimension, and then spatial information on the other dimension along the slit. And with the polarimeter, this is what allows us to get hopefully the magnetic field measurements. So this is again, it's a challenging instrument. It's really quite large, 4 meters here. And so just to give you an idea of what the gondola looks like, this is a flight of a different instrument, an X-ray instrument, I believe, on NASA's balloon. And if you can just kind of imagine, this whole truss structure would be replaced with some sort of structure with our instrument here, and a lot of mechanisms. So the lenses have to move when you switch between wavelengths, and we have to correct somewhat for roll. So this whole thing has to roll, and we're kind of in the middle of our internal study right now, and hopefully we'll be proposing in August 2020. But it looks challenging, but exciting right now. And so this is a future pathfinder, hopefully for a spacecraft down the road. So I just want to thank everybody. In particular, there were kind of too many names to list, but the NCAR Research Aviation Facility, all the technicians and mechanics and who helped us. We wouldn't have been able to do the 2 flights without them. Here's a picture where you see probably a lot of familiar faces from the 2019 Eclipse flight in Lima, Peru. And I'll take questions. Thank you.
Thank you, Jenna, for this very interesting talk. So we already have some questions, and the first one is from Scott Sewell from HAO, and he actually submitted this question several minutes ago, so you touched on some of the questions already in the remainder of your talk, but I will still read them to you, and it's actually two different questions, so I will do one first and then the second one. So he writes, great to see you again, and thanks for a really interesting talk. Which of the IR lines you're attempting to measure has the greatest predicted magnetic sensitivity? That is, which are you most hopeful that with sufficiently strong signal to noise and use as a diagnostic tool for measuring corona fields?
Okay, that's a good question. Hi, Scott. It's nice to see you too, virtually. Let me go back to the line list. I believe it's sort of a competition between two lines, this iron 13 line at 1 micron and this silicon 9 line at 4. Actually, this question of which one of these is going to be better is part of the reason that we were originally going to do the balloon instrument with just this 4 micron line, but it wasn't clear that that was really the best choice. This one has a longer wavelength, which makes it the signal is larger for a given magnetic field, just the line splitting. But because it's a weaker line and you're going to have a lot of background, it could be that the SNR advantage from this one actually wins out over the splitting advantage from this one. So it's a question, but those two I would say.
Okay, and the second question is, what altitude do you need to fly at to get above interfering atmospheric absorptions for these measurements? Would flying on a high altitude balloon help?
Yes.
So there you go.
Thanks, Scott. Yeah, so I guess you asked that before the balloon. Yeah, if we go back and look at the atmosphere, let's see right here, you can see that we're kind of in the 90%, clear range. Well, except for this region right here. This is at 43,000 feet. At a balloon at an altitude of I think probably 150,000 feet or something like that. I don't know the exact numbers, but I would imagine it would be much closer to 100% transmission.
Yeah, thank you. So while we wait for more questions, if we get some, I'm going to ask a question, and I'm not an expert on this, so I'm just asking a really dumb question probably, but you said that you get some more time out of flying on the G5 as opposed to being on the ground, and I was just wondering how much time does that buy you?
That's a good question. Well, it buys us about maybe 50% or a little less, 40% maybe. It depends a lot on the wind. Because the actual ground speed, of course, is dependent on the wind. So in 2017, it was I think a 2-minute and 40-second eclipse on the ground directly below us, and we got about exactly 4 minutes. In 2019, we were predicting something like an 8-minute eclipse in the G5, and because of the tailwind that we had, we got something like 9. So the wind makes a big difference, but yeah, on the order of 50%.
Okay, well, I did not get any more questions, so I would like to thank you very much again for giving this presentation. It was very, very interesting to see all the difficulties you had to deal with flying, but then actually getting something out of it. So yeah, thank you very much. If I get more questions, I will forward them to your email.
Thank you.
And yeah, with that, thanks again, and I hope we will get to see you again soon.
Yeah, thank you so much for the opportunity to speak. I really enjoyed it. Hope to see you soon. Take care.